Yep.
I'm just hoping that way, because I made a deal with them that I couldn't win money if I win, but I could get money if I lose. How do you do that? Because I can't get money because of college. And so, oh, right. But I wanted to play, so I was like, I'll buy in, but I just can't win. Or like, I can't get money. So I really don't want
Okay, welcome back. We had a good break. And now we get the short wrap up of the semester. Thanksgiving's really late this year, and so we have for this week, there's one homework due that does some material from the tables and a logistic regression problem to see how that goes, get some experience with that. But primarily the thing to work on is the project. So hopefully over the break, or for some of you before, finding a data set, finding a topic, getting the data into R, getting kind of an outline of thoughts about what you want to do with that, starting writing, starting analysis. If you submit to me, drafts, I'll get some feedback this week on that. Coding can take a little bit of time to get things going, to work on, you get funny errors or something. It's good to get that done. So whatever you can do early this week will make it easier toward the end. And then we'll we'll have presentations during finals week, during the regularly scheduled time for finals. Right? So before break, we talked about logistic regression, where the y's are zeros or ones. Right? So yi equals 1 or 0, with some probability pi sub I or 1 minus pi sub I using the book's notation. And we model a transformation of those pi's as a function of x's. Right? And so we want to estimate these probabilities. So we do the log of pi over 1 minus pi, that logit transformation through this logit, so-called logit link. Logit pi sub I is that as a linear function of x's. Theta 2, xi2. Right? And what this next chapter does is the same context, but the x values are repeated. So you have binomial data, right? So the x's you have pertain to a group of observations, and so we'd have more chance of looking at model fit and residuals and things like that. When all the data are ones or zeros, and we're predicting individual probabilities, residuals look a little bit funny, that they only can kind of go in a certain case. In this case is multiple observations for each level, right, of x's, right? So that we can look at that. And so, yeah, it's called binomial. Some people call it binomial regression. To me, I really think about it as logistic regression with repeated observations and x's that pertain to groups of observations. So it's very much in the same context, right? So when it's binomial data, y sub I, what we're going to observe is binomial, random variable, a certain number of observations, and a probability of success for one of those observations here. So it follows binomial probabilities. So mi observations, yi then is some number 0, 1, 2, up to m sub I in here. And pi sub I is the probability of our occurrence, so-called success or whatever it is that we're looking for, probability of success on one trial. And the m observations, to be binomial, we assume these things are independent, right? So the i's then could define areas, regions. They could define, centers. If you have different treatment centers for a disease, they could be, you could maybe have multiple observations on one individual. the observations you might not think of being as independent there, so that might kind of violate the model, but it might be close. And so now the logit, of this pi sub I is still, I'll just drop the I here, beta 0 plus beta 1 x1 plus beta 2 x2, and these two x's, these are relevant or pertain to all m sub I observations for that I. And I guess maybe it would be useful to put i's on here to make that statement. So I sub 1, I sub 2, right? And the coefficients, the way we're interpreting coefficients in the logistic regression is if you take e to a power, right? If you exponentiate this, you'll get pi sub I. Well, to get the exponentiate the e to that, you get pi sub I over 1 minus pi sub I, then is e to this, beta 0 plus beta 1 xi1 plus beta 2 xi2. So if you do a 1 unit change in one of the x's in x of I, say, then in e to the, oops, quite get that to go, right? Then the impact is e to the beta j multiplies, so one of these, e sub ij, right? So jth variable. Multiplies the odds over there. So if it's positive, the odds of the outcome are going up. Right? And if b sub beta sub j is 0, right, then it's an odds of 1, then there's no change. So a coefficient of 0 or an e to that power of that's 1 means that there's no change in the odds as x is changing. Right? And in a multiple regression with multiple x's, it's always interpreted given that the other variables held fixed, right? So if we're considering x of 2, what's the impact of this one? Well, for the given level of x1 that we have, if x2 is changed by 1 unit, right, then you would multiply the odds there. Sometimes it's not realistic to change x1 without changing x2, if they're correlated, but that's how you have to think about that. Right? How would you know if this is reasonable to use this model? Well, in linear regression, we could do a scatter plot, right? Before, when we had plots, we only had zeros and ones. So you can kind of see, is there mostly zeros versus, right? So just logistic, if y sub I is 1 or 0, plotting y versus x, all it can do is produce a plot that looks something, kind of like this. And you get kind of an idea that the probabilities would increase, but it's a little bit hard to see. But in the binomial case, we can do just kind of a simple estimate. Right? We can do a sample proportion. And then we can plot that sample proportions versus x. Right? And so if we get enough, large enough sample sizes at these, and there really is a model, so here's x sub I, and here is p sub I hat, then you might see, these things won't be exactly on the line. Right? You might see something kind of going up like that. The logistic regression is going to fit kind of a wavy curve once we undo the logit transform. But you get a little bit more of indication of is it going to actually fit that curve. You could actually plot, this will be curvy. You could plot the log of pi I hat over 1 minus pi I hat here versus x of I. And if this fits pretty well, then this thing should be pretty linear once you straighten it out. And what's above the curve here would be above the curve after you do the transformation. So you can make a plot that makes it look like that. You do run into a problem with some of these plots, with this logit anyway, that if some of the y sub i's are 0 or m sub I, right, then that doesn't work with 0 or 1. Because if it's 0, you're trying to take the log of 0, or if it's 1, you're dividing by 0, and that doesn't work. So a fix-up would be to add something to the numerator and denominator to make it so you can calculate something, right? So the log of pi sub I over 1 pi sub I, these hats in there, well, this was y sub I over m sub I, and this is 1 minus that. And if you multiply the numerator and denominator by m sub I, you get some cancellation. Well, to simplify to that ratio. So the number of successes over the number of failures is this logit. Right? If these ended up being, zeros or m's, right, and so you can't calculate that, you could replace it by y sub I plus 0.5 and m sub I minus y sub I plus 0.5 as kind of a fix-up to that, right? It makes it so that if it's 0, you're going to end up still with a very small number. If it's m, you're still going to end up with a pretty large number, but it's not going to be 0 or 1, so you're not going to run into the problem of that. So you could plot this thing, versus the x sub I. If sample sizes are really small, if the m sub i's are small, you might group some x's together. Right? You might do that in logistic regression anyway. Right? So we're plotting this, and this is done to look for linear. Pattern to suggest that you might want to use one of these models. Or it might be, for communication purposes, to illustrate that it's an important predictor. If it's a steep slope, you would see it there. Right? In general, for logistic regression, if you want to try to make a plot, you might make bins of x's. So we're plotting. So if each of the m sub i's was 3 or 5 or something like that, there's not a lot of say they're all 3, you're either going to get 0, 1/3, 2/3, or 1, and there's not a lot of variability that's shown there. But if you grouped, say, the lowest 3 x's together, then you'd be up to 9 observations, or the lowest 5 x's together, you'd be up to 15, and you would see more variation. So if the original data, were a bunch of, it was pretty kind of dense, kind of a little sparser, and then zeros and ones, and the other ones were kind of out here, like this. You can't really see too much, but if you kind of group these together, and then make this a bin, and this a bin, right, and some of these a bin, and maybe something out here, you would end up, and then you plotted where these estimates, so these estimates all would be here. These estimates would be kind of climbing a little bit. This one looks like it's kind of high. This looks like more kind of middle, and then kind of high. So you would start to see kind of an increased pattern. To do anything like that requires unique coding. There's not a standard function that says group these things. There are kind of smooths or splines, or there are some graphic things that help you see that. But in my experience, not knowing those off the top of my head, I usually end up just kind of grouping things. Right? So we have a model. Right? The logistic model that has these probabilities that are related to x's. Right? And there's not a direct solution to find optimal x's, but maximum likelihood, optimal coefficients, maximum likelihood estimation, Excuse me. We can write down the probabilities of the binomial models, substitute in the betas, maximize that with numerical techniques, and so that these are MLEs, so we get beta hats, right? These then can be used to produce pi hats for these different things. And so that's our fit. We can graph the fitted line, at least with one x. You can get predictions based on multiple x's. And so the question is, how do you assess fit? So two things that we can do. Right? One is assess fit of this logistic model. Do our predictors, how in the way that we've used them. If you put them in as linear predictors, maybe there's an interaction, maybe there could be squares, terms and so on. There could be variables we've left out that would be important to describing things. Some things we might do a cut point rather than a straight linear. So we could assess the fit of the logistic model just like we did with the linear ones. And then we can do some testing of coefficients. Are any of those betas really possibly zero, or are they statistically significantly different from zero, in which case they would be significant predictors, right? So we're going to do two things with this binomial one that we can do, that we like to do with ordinary regression, right? But it's a little bit different formulas. Right? We can calculate residuals in a couple of ways. Something called a Pearson residual. Right? Is yi minus m sub I pi sub I hat over the estimated variation from the binomial model of that expected count. Here, the pi I hat. If you undo the logistic transformation, I'm just going to write it with one x here just to save some space. But once you calculate the maximum likelihood estimate, the transformation that goes from the logit back to the probability scale is this information, this transformation. Right? So this would take yi minus the expected value given this estimated probabilities. This is the binomial variance, and that would be one type of residual. The R and other things often report something called deviance residuals, which has to do with a log odds ratio. Right? This formula is a little bit. So this is one alternative. So we'll show the formula on the next one. But what you do with these residuals, right, is you're looking for residuals that are bigger than 2 or bigger than -2. Those are, you're taking a difference from a mean minus a standard deviation. So usually 2 for a normal scale, or most t scales, right? If it's bigger than 2, less than 2. If it's the biggest one out of the bunch and it's 3 or something, it's very possible that that observation doesn't fit so well. So look for residuals. Absolute value of residuals greater than 2. Possibly those points are not fit well, and you might want to look for some other explanation of why they're just different, or maybe the model doesn't work so well out there. The deviance residual is the book gives the formula. It's the sign. It's a signed residual, which means you calculate: is it positive or negative? Is the observed value above or below its predicted value, right? And then there is a big square root. If I get the whole thing over here, 2 times y sub I, the log of y sub I over its expected value, plus m sub I minus y sub I times times the log of m sub I minus y sub I over m sub I minus its expected value. Good. And then squiggly bracket over there. So what in the world is this thing doing, right? We had a chi-square statistic for testing tables, right? And that generalized likelihood ratio chi-squared had observed times observed over expected, right? So this is for the successes. This is the same thing for the failures, right? This is the number of failures kind of that we observe. MI trials, YI successes, so that's the number of failures. So the number of failures, and this is the expected number of failures. Right? So it's kind of like that, the thing that goes into the chi-square statistic. If you look at the part that's inside here, inside the squiggly brackets, this is log to a power, and this is, well, anyway, it's something times a log. So the y sub I can go up top, and this is m sub I times the log. So the m sub I can go up there, and it's adding two logs, so you can bring those together and make a multiplicative. Right? If you do that inside the curly brackets, you get log of this ratio, yi over mi pi hat, raised to the yi, and this one is then this thing, mi minus yi over mi minus mi times pi hat. That thing raised to this one over here. Right. So it's log of all of this. And if you divide by mi over mi, right, where you get yi over mi, that's our pi hat. We're not pi, it's kind of pi bar. Right, it's kind of the average of those. It's not from the model. So you can rewrite this part. Oops. That's not what we needed. Oops, we don't need that. There we go. Okay, I can touch it, get some static electricity out. Right. So it is, so pi bar over pi hat, this thing raised to the yi power, and this thing is 1 minus pi hat over 1 minus pi bar raised to this power. I'll clean this up just a bit, right, and get rid of those extra lines for the record. Right. So this log goes over this whole thing, where here the pi bar is just the sample average that's in there, right? So it's kind of a log odds ratio with certain powers in there. Right? This is actually something called the Kublak-Leibler information measure, comparing these two probability distributions. Right? So Solomon and Kublak information measure. There's a field of stuff called information theory about communication. It goes back to communication. You're sending bits of information over a noisy channel, trying to extract the signal, and there's kind of a model for what's coming out and then what's observed. Or this is used to compare two probability distributions and how close they are together. So it ends up being a deviance statistic that can be used to compare these two. And so again, if this thing is bigger than 2, right, or bigger than -2, it could be negative, right, then you would think that that particular point does not fit so well, right, by that, right. These things have other uses, these deviance residuals. They're key to one test of models. But any questions over this big old formula? Right? So you're going to have the y's, the number of successes, and this. You're going to fit a model. Or you're going to get predicted for that case. and then go through this calculation to get this deviance residual. And any of those that are bigger than 2, less than -2, that point, that particular group would seem to be different. Right? If these are centers in a multi-center trial, defines the different groups, maybe one of the centers just has a different patient population than the others. Right? Or if there's different schools, right? Maybe one of the schools is a magnet school, or it's a school that's particularly struggling, right? And those particular schools would stand out as not being, their performance would not be explained by the X's in the model. So there might be other particular concern for them. So the other thing there, let's say our, we can use this for testing. So our full model would say that the logit of p sub I is just simply an alpha I. Right? If I goes from 1 up to 10 centers, right, then this thing has n parameters. Right? It's a full model, it's saturated, every group gets their own probability. No reduction of complexity based on how it relates to an X. Right? A reduced model is a logistic regression module. Say logit of pi sub I is beta 0 plus beta xi1 plus beta 2 xi2 plus possibly beta p xip up here. Right? So this looks like p plus 1 parameters. Some books will pay p minus 1 or p minus 1 up here, and I just have it be slightly different. Right? The deviance of is for this model is the sum of the square deviance residuals. I going from 1 up to n of the deviance residual for case I squared. Right? If the null hypothesis is this reduced model, and the alternative is the big full model that has extra parameters. Right? Presumably there's more parameters up here. N is bigger than p plus 1. And this is the alternative. Right? Then under the null hypothesis, this deviance under H0, the deviance statistic here is distributed as a chi-square random variable with n minus p parameters. Right? And I'm wondering if there's a minus 1. But anyway, it's like that. But so just to make sure, we can double check that exactly. How does that correspond? Is it p plus 1 or is it p minus 1? And so if we get a large value of the statistic, that means some of the residuals are big. And if it's big enough, it's bigger than the 95% cutoff for this thing, we reject the null hypothesis, which means that this model is not adequate. It doesn't fit, right? Which would mean that you need the bigger model to fit. But if you don't reject, then this model would seem to be a reasonable description, right? Right. Would be one possibility there. So that's overall, we can test whether there's that fit. You can also do individual coefficients, right? So if you had one big model and had its deviance, right, and then had another smaller model that left out some of the parameters, then you could do the change in deviance as a model. So here's a small model, and here's a big model, and change of d equals the difference in number of parameters. Then and this one has a deviance statistic on this one. This one has a deviance statistic under the null model. The deviance statistic, which is based on the residuals, is going to be smaller under the alternative. Right? alternative should fit better, it has more parameters, more variables, right? So the residual should be smaller, so deviance should be smaller. Oops, let me change, make this a df, change in df. Right? So the change in deviance is going to be the deviance under the null model minus the deviance under the alternative, right? And if under the null hypothesis, right, we'll reject the H0 if the change in deviance that we see is greater than a chi-square, the 95th percentile of a chi-square, where we have the change in degrees of freedom. Right? So kind of like a nested f-test, right, for regression, comparing models, right? You can do that. So that this deviance residuals comes into this test comparing different models. Kind of the final thing, right, is that we'll say is you can do a test of an individual coefficient. Is an individual coefficient 0 versus not, right? In the output, there's going to be individual z statistics and p-values. Well, those for our testing is one coefficient 0 given everything else that's in there. Right? So our z statistic is going to be just this over the standard error. Right? And so we reject the null hypothesis if our z value is greater than 1.96. These data aren't normal, right? The y's weren't normal, so we don't use a t like we did for the ordinary linear regression. Right? And so let's look at so we can test individual ones. This would be for one coefficient at a time, but that previous one, right, for comparing models would be useful if you have, say, indicators of geography or indicators of multiple groups that are there, or some multiple treatment factors that are incorporated, so testing them all together. Right? So you can do a lot of the same things that you do. Formulas end up being different, and it ends up being deviant. Things look funny often with residuals if you have smaller sample sizes in each group. If you have large sample sizes in each group, it looks a lot like ordinary regression. So let's look at some examples. So the first one we'll look at is in chapter 21. Here is some data. There are different islands. And the area of the island is there. And they have the number of bird species that are at risk on those islands and the number that have gone extinct over a time period. And I ran out of time this morning to review exactly all the details about these applications, so I'm sorry I can't get much more insight of that right now, of those. But we want to look at is the probability of being extinct, going extinct, related to area. Right? Small islands, this is relevant for global warming now, as sea levels rise and resources become depleted. Will small islands face catastrophic extinctions, right? Whereas larger islands are still able to, things will change, but they have more land area still to keep supporting. Right? So let's look at proportions and put the C-bind, put these on together. So here's the proportions that come out of this. So this area that had 185, 5 of the 75, so that's extinction rate of about 7%. Plotting those proportions, they kind of range from 0 up to about 50%, right? So that if they were all, 0 to 10%, that's a pretty narrow range in which to predict. But this has some pretty good variability in terms of the range. Hopefully we can explain some of that variation that's in there. Here's the kind of overall average, right? Just adding up all the birds and the number that are extinct, the cumulative average is about there. can plot the area versus p hat. That doesn't really look great for plotting, for predicting. Right? It's kind of low up here, and then you can't hardly even see much variability in there. Right? So, a linear regression would kind of go through there, and again, logistic won't work so well. But if you do log area, it spreads things out, and even that's starting to look kind of linear. Right? You could do logistic plot area. So we can be smart about this, right? So we can do a logistic function of some p, and this is the log of p divided by 1 minus p. Right? So now if you do logistic of, say, 0.5, it gives a value of 0. Right? Even odds, so. Right? If this is 0.75, it gives you another value out, or 0.25 is going to give you a negative value there. So we can plot, say, log of area versus logistic, I could have called logit, I guess, of p hat. And so that's the logistic transformation. That looks, pretty reasonably linear in there. Right? Could be very useful for communication. And it looks like in this I've gone on to the next case. Let's look at another plot. So in this one, there was it's an experiment that has to do with the colors of moths. So there's light and dark moths. They're placed a certain distance from distance to Liverpool, England, right? So they're placed someplace, and the eggs are placed someplace, right? And then they come back at some time and see if they've been removed. So again, I don't remember exactly the details, but something like this could deal with predation. Near Liverpool, there's more smog that covers them, so the light ones don't look so light. Near the city, about the countryside, they're more distinct. Right? So let's get an average for that. These are what the averages look like. Distances, right, as a planned experiment. This is the variability. So there's some variability we can try to predict in these proportions. Right? Kind of same story. Here's the average is right in the middle. And this plot, there doesn't seem to be much of an advantage of taking logs, right, in this case. On the original scale, it's kind of nicely separated, spaced out, so I wouldn't think about really taking logs of this. And you could do the logit transformation, that's probably better. So, this doing the logistic regression, the binomial version, right, is we don't want to create a data set that has rows of zeros and ones. You could. You could just create a data set where you replicate it, 56 times. Light, 0, 17, yes, 39, no. So you could do 56 rows, but it's not actually necessary. Right? You could replicate these and get all zeros and ones and just write ordinary logistic regression. But because this is so common, you can do this binomial regression, and there's an argument called weights. Right? For the species one, the counts was at risk, right? The number of species at risk. Right? So it will recognize that you're putting in proportions, right? And there's groups, and this is the number of observations per group. Versus one has no predictors. With this one, it has log area as a predictor. So here's this first model, and here's this next model. If we summarize the base model, right, that had no predictors in it, deviance residuals here, there's some that are -3 up to 2.6. So there's a few of these points that will really stick out. This estimate of -1.5794, of course it's not going to be 0. If you do undo that transformation, you get 0.17, which was about 17% of the species overall were going extinct. Right? data set, case 2101, the names on that one, so you do the sum of extinct over the sum of at risk. Extinct, right? You get 0.17. It's almost like that. You know, there's a little bit of errors. So just looking at the base model with with just an intercept, right? The estimated intercept is basically the proportion in the data set that's there. Right. The second model, right? What else just comes out of that? Right, that one's significant. The deviance that it calculates is 45.338. That's just the sum of the deviance, the squares of the deviance residuals for that model. The model with log area, right, gives this output. Now deviance residuals are all quite smaller, right? When it was just the intercept, some of those deviance residuals were -3 or 2.6. Now the biggest ones they're all less than 2 in absolute value. That's promising. Right? The test is the coefficient on log area significant. Right? The z-value is -5.4. It has a formula for the standard error. Right? And so the p-value is very small. So it's highly statistically significant. We don't believe that that's 0. And that's a significant predictor. Log area is a significant predictor of that probability there. And the residual deviance goes down to 12. Right? So there's a drop of about 33 points there. Right? So we've added one. Let's see, ANOVA applied to these things, calculates the change in deviance for us. There's a difference of 1 parameter between the models. We've just added that slope. Right, so it's a chi-square 1 test, right? And so we get a tiny, tiny p-value. It's not quite the same p-value as that one, but you know we're dealing with very small numbers, so not too. Maybe 2 times that. No, it's a chi-squared, so it's just the upper tail. Everything's already squared, so we don't need to multiply by 2. You can do confidence intervals for this. It has a called profile likelihood. So there's a confidence interval for the coefficient, the multiplier of the logs, right? But that's on a linear scale, right? To get it back to the multiplying odd, you just exponentiate that, right? So this is the multiplier of the odds ratio. So as area is going up, right, odds are going down, right? Because the multiplier is less, right? So bigger islands have less extinction. Right? And there's a 95% confidence interval for that. You can pull off those different individual pieces, right? Like the deviance for that model, degrees of freedom. There's something called extra binomial variation, right? So that we haven't really talked about. But in these type of things, people do worry about that. And the book has more discussion. We're not going to have a lot of time to discuss that, but that would be a more advanced topic. So the idea is that the observations, for some reason, in some of the areas, could have something that doesn't quite follow the binomial variability. Right? So the binomial assumes, for instance, that there's constant probabilities in each area. So perhaps P sub I does not apply to all M sub I observations. Maybe the species within a particular island are big or small. So there's a survival rate for small ones and there's a survival rate for big ones, but we've put them all together. So there's extra variability because we don't know something about it, right? Perhaps the observations, survival is not really independent in area I. So if one species goes, then the next one goes. So they're not really independent of another. Right? If the one that you eat as your food source is gone, your chances aren't so good, right? So that could cause some positive correlation, could cause more variability. And so the model might not fit for that, right? And to estimate that, we can look at the deviance over the degrees of freedom. If that's much bigger than 1, then that's an indication of possible extra variability. In this case, it doesn't show up, right? So the kind of comparison is we compare the deviance for a model over the degrees of freedom that's associated with the residuals, the number of observations, number of groups minus the number of parameters that are there. And so if this thing is much bigger than 1, then possible issue to deal with. Right? There's different ways to deal with this. You can get more hybrid models. You can get more data on which species were going extinct on different islands or at risk. You could include species-specific information, or at least if you could break them into, mammals, amphibians, birds. Well, I think these are all birds. You could include another variable and break it out, and that might take care of it. Maybe you have another predictor variable you can put in, like elevation of the island, right? Or distance to another island, or something like that. Right? That might explain it, and then the extra variability would go away. Right? Or there's bigger models that would explicitly have more variability. You can put in an extra parameter that adds more, kind of multiplies. Get a multiplier of 1.2 onto the variability and fit that in likelihood. So it changes what you get as results. We're not going to do that right now. You can plot. In this case, it was 0.75, so it's not really a concern. If you plot this, it makes four pictures. Right? So I only have one screen open. So here's the first plot. I think distance here's the first plot it makes. Residuals, deviance residuals versus fitted values, predicted values in that model. Right? And is there much of a pattern? It's kind of a smooth line that shows how these, you had to fit a kind of a smooth line to the pattern of residuals. Kind of tagged a couple of the observations is a little bit bigger. But again, all those are within ±2. No big pattern really shows up, so that's fine. That's the first plot it gives you. Are the residuals normalish? Right. This kind of a curve. This one's always often a little bit difficult to use, right? Because if you have small sample sizes, like if you only had 3 per group, you're going to get 0, 1/3, 2/3, 3, 1, minus the predicted values, and it's not going to look normal. Right? The fitted values are going to be kind of at different levels. Right? And so it's not, well, maybe it's not too bad for this size of the data set, but it's not going to be perfect. If you had very different size groups, right? And some groups that just completely didn't fit at all. Based on that variable, you probably get a funny pattern here, like a big residuals sticking out, like that. The next plot is this one, predicted values versus, it's kind of looking at so standard deviation, absolute value. So standardized deviance residual, absolute value, square root. So it's kind of looking if there was more variability, if variability was changing. It's kind of changing a little bit as you get along there. But so there'd be a little bit of another thing to do. This would be also related to the extra binomial variation. And then leverage. Are there particular, this kind of a Cook's distance is a function of the x's, so area in this case. If there was one of those islands that was massive in comparison to the others, it would be way out here and probably be identified as outside these bounds. But it doesn't look like it's abnormal in any way. So that's there. If this was your field and your area and you were fitting these data, you would learn to use those a little bit more. So that's this plot. It seemed to fit pretty well. So if we plot the logistic, if we do kind of a log area versus the fitted values of the mod 1 extinctions. Right? kind of, this is how the probabilities are going down. Right? And these are this is not exactly straight, this is a slight curve to it. Right? But it would give, trying to preserve species on small islands, you have more work to do, I guess. How about this one with these moths and the treatment? Let's fit a model here, one that has, and again, the weights in this case are the number of moths that were placed, the eggs that were placed at a particular location. Right? Our basic model would have distance, and then is it light or dark color? So, right, put that in there. And maybe a second one I'm going to put in is, that, you get some of the interactions of those things. So the summary of this one model. Right. The light colors have a negative coefficient on the linear scale. Right? So that means that its chance of survival or staying there is less. Right? It's going down, and it's highly significant. Distance is not a significant predictor. It would have survival increasing as you get further from Liverpool. Right? And that, which would mod 1.1 here. Those are confidence intervals for those, and if you exponentiate those, you get the impact, say for morphology, from going from light to dark, from dark to light. Right? If it's a light one, the chances of the odds of survival are about half to about 88% of that. Right? So you can convert that back into probabilities if you wanted to say how the probability is changing. So, but you can do that. And then this one, the distance was not significant. It includes, it's all very, it includes 0, it includes 1, so in that interval. And it's also very close to 1. So even if it had shifted a little bit, a 1% change in the odds ratio is not going to produce much of a change in the probability. So even if it had been significant, it might not have been that big of an effect. Comparing these versus the null model, it's significant, right? So the null model just had intercept. The other one had 2 variables, so you get 2 coefficients there, right? You can look at plots, distance versus, that's the original data. Here's the light and dark ones. This is kind of just picture the data. I don't have the p hat, the fitted values, right? So let's see, what's the p hats? You can do kind of a point. Let's put the points on there. Distance is going to be the same predictor. And then fitted of, it's called fitted of the mod warranted REM. Right? And then what we'll do is put it back on the probability scale, because the x-axis here, the vertical is on the probability scale. Right? And that's the inverse transformation, and let's make these points fit, that goes there, make color equal red, so it stands out. Right? So say fit there, and it didn't work. Maybe, no, I don't think I think it's already on the probability scale. Right. Yeah, it's already on the probability scale, right. So you're getting under the model without any interactions, right? It gets these 2 lines here, right? And I suspect if we put the colors in different, it would look funny. Let's see how let's see, it's getting pretty close. The second model, is there an interaction of this? And make it a little wider so we can see that a little bit better. Is there an interaction between morphology and distance? It looks like there is. Right? It looks like there's a significant interaction between those. Right? Now, depending on how I read texts about advice about regression, I get different kind of interpretations of what to do. Some books would say you look at main effects and then look at interactions among main effects. Right? So if you kind of do a forward selection, you would go that way, right? And you might not ever try this one, because you would say, oh, distance isn't significant, I should take it out of the model and only look at morphology, right? But if you look at the other way, kind of backward selection, put a big model and then take out what's not significant, you start with this big model and say, oh, the interaction's significant, I should keep everything in, right? So I think even, an important variable, if you're trying to build up models going forward, you might think about starting at a bigger model and going backward, because you can then find some interactions that you wouldn't find just building up from below. The difference between this one, well, let's see. Here, because the z-value of this test is significant, it's a significant interaction. We kind of expected some of that from this picture, because light's up here and then goes down, whereas dark is here and then goes up. Okay. Across, so we expect that. The deviance test, right? Comparing the deviances, the value is 11.3, right? And so that's a significant there. Confidence intervals on the linear scale and on the impact on the odds. So that looks small. So, to do the change, right? If you change from light to dark, you have to do it at a certain distance, right? Because of the nonlinear things, it's just not additive, right? So it's a little bit more involved to do that, but these are confidence intervals for the individual thing. And distance, changing it by 1, maybe it's not so interesting, but a change of 10 kilometers might be more interesting, right? Certainly that's what they're doing in the experiment. So you could get a prediction of light moths at one place versus dark moths at one place and at a certain amount of distance. So you might do, at 10 and 40 to try to, you work out a couple predictions of different, because you have the two variables there. So let's look at just the final plots. Was there any extra binomial variation in here? That was thinking to be 1. Residual difference over degrees of freedom is 1.3, so no, not too high. Right? So plot of this one, right? There's those patterns. The second ones that are plotted, the x's, see the second model, right, gets this interaction between this is the dark, surely, and these are the lights. Right? If you do the diagnostic plots, right, this is going to give our 4 plots here. So the residuals from that first model that didn't have an interaction, right, there's kind of a pattern to the residuals. There's some residuals up just at that level of 2, -2. So we kind of worry about fit there, legitimately. Normality doesn't really show us anything. Scale location. Well, these things are kind of large, I guess. Above 4. This one has some things that seem to have a little bit more leverage. So maybe a few of the larger distances or smaller distances you'd have to check. Okay, points 3 and 4 are kind of the smaller distances, so there could be kind of a bigger effect there, perhaps. If you do that, though, with the second model, right? Oops. Right, here's the second plot. This one doesn't have much of a pattern in the residuals because we've included that interaction. It fits much better. And they're, except for that one, less than 2. Having one stick out out of a few is, you kind of can't get all of them. Right? That looks much better. Still, that seems fine. This one, I guess there's that 7. There's still that one that stuck out a little bit better. So that maybe something about that location, maybe it's closer to a road or closer to a swamp or something, right? Biologically, you got to look at the whole picture that there might be something you're not accounting for. And in terms of the leverages, right, the 0.5, we're inside of that, so it's less concerning. There is a package in R for extra binomial variation. That if you load that, can fit that. And it has a little bit of impact on the z-values and so on, but they were very significant, so it doesn't change that. It's essentially estimating an extra parameter, allowing for more variation. Right? But I'll let you go through that on your own if you want to. So there are ways to go. Some of them are in packages, in books on discrete categorical data analysis. We go into the models and how estimation is done in those in more detail. So we have Wednesday. I'll show you another example on Wednesday, and then Friday we kind of do some wrap up and summary and talk about how we want to schedule presentation. I'll be available this week to talk about presentations, projects. Yeah.
Just to clarify, the homework for this week's due Friday, right?
Yeah, you can have it on Friday.
I'm gonna try to look at some of the sets tonight. That's helpful. Or at least tomorrow.
There you go.
At the very latest.
Just listed, kind of listed out nice and beautiful.
I don't know, we could always like, maybe find like some stock market data or something, like,
I'm gonna
that would
use the
definitely-
Rockies one.
I was doing time series, so
Oh,
maybe we
right.
could totally have other, I like, what's
They're
this?
home and away.
Another one.
Just a good one.
I have the set
Yeah.
and some stuff already done.
I think